I want to return to the example that we did of parameterizing a cone, and this was the cone that we looked at, the parameterization of it in the last video with Dr. Bassett. And I would like to add to this the language of transformations. So when we gave the transformation before, we used the function r, and I would like to use t just so we don't get the letters, some of our letters confused. So I'm going to let u be this, or r be this transformation t, and I want you to think of t as a mapping from r2 to r3. So we're going to call t, you could call it a function, but we're going to call it a transformation instead. And usually we use the word transformation when we're moving from one space to another space. And so based on what we saw in the previous video, we could give the transformation from one space to another that would give us a cone by saying the transformation from u to v was given by these three coordinate functions here. So the first one was u cosine v, u sine v, and then just u. And this was for 0 less than or equal to u less than or equal to 3, and 0 less than or equal to v less than or equal to 2 pi. So the first thing I should say is that I'm using v in place of theta, and I'm using u in place of r, just to make this a little bit more generic, because oftentimes when we talk about a generic parameterization, we use the variables u and v as opposed to r and theta. So the next thing I want to look at is how we actually consider this parameterization as morphing the uv space into R3. So here is this uv space here. Here will be my u-axis, and here will be my v-axis. And you saw this in the video, although Dr. Bassett used r and theta. And so we saw that, okay, u is going between 1 and 3, so there's 1, 2, 3. So there's that. So u values will range between 0 and 3, and our v values range between 0 and 2 pi. So let's just put a few of these up here. Let's put, there's pi, and there is 2 pi, and if we need other coordinates, we'll include those tick marks. So our region that we were morphing is this green rectangular region here. And this is something we're going to see in some other work in a little bit. But I want you to recognize that even though we're talking about something that's going to be morphed into a cone, we are starting in this case with a nice rectangular region. Then we're going to do the transformation t, and what I want you to think of t as doing is maybe it's like a origami instructions. It's going to tell us, t tells us specifically how to fold this rectangle and then place it somehow into 3 space. So here we have the cone in 3 space that we were looking at. And so now we've got this morph space up here. And let me bring this up just a little bit higher there. Okay. So here is our x-axis, here is our y-axis, and here is our z-axis. So again, what do we mean by this transformation? It took something from R2, this was our uv space, and we moved it into R3 based on these folding instructions here. And the reason why I'm doing this, folks, is we're going to need this for some other work that we do in this class. So I want to focus on how this transformation actually worked. So the first thing I want to do is let's look at some point that was on this in this domain space, and I'd like to look at the point 3/2 pi over 2. So that would be this point right here approximately. Oops, come on. All right. That would be this point right here. There's the ordered pair, 3/2 comma pi over 2. And we do the transformation to this point, and we put it into 3 space based on this collection of rules here. So let's look at what the transformation does to this point. And if we actually plug these coordinates in for u and v, notice that the new x-coordinate is going to be 3/2 times the cosine of pi over 2, but the cosine of pi over 2 is 0, so the new x-coordinate is going to be 0. And the new y-coordinate is just going to be 3/2, and the z-coordinate will be 3/2. And so this is going to get mapped to this point right here. Let's move that down just slightly. So this is the point that got mapped to 0, 3 halves, 3 halves. That's this point on this sphere. So the transformation said what to do to this point, and it brought it from this 2-dimensional space to this 3-dimensional space. There's some other things that we can sort of keep track of, folks. So let's focus out here where we have the line where r is equal to 3. So this right here is the line r equals 3. And I'd like to go ahead and let's look at what the first half gets mapped to and then what the second half gets mapped to. So this first half of the line r equals 3, well, r equals 3 on the cone is the upper part of this truncated cone here. And where r equals 3 between 0 and pi, that's going to be this half. Let's see here. That's going to be this half of that top of the cone. And the next half, where theta varies between pi and 2 pi, will be this half of the part of the cone. So this line right here, all of the points along this line, and this is just the line r equals 3, that vertical line there, it gets morphed to this point in space here. So this end, in fact, this end right here gets connected to this end right here, showing up at that point right there. Okay. Likewise, let's look at a couple of other points on here. So let's look at a line, a horizontal line. So maybe here we have the horizontal line. I'm trying to put it in the right place. Maybe that's the horizontal line pi over 4. Okay. So where does this horizontal line get mapped? Well, notice that this horizontal line at pi equals 4, it corresponds to all points where the radius of the cone varies between 0 and 3, but the angle stays at pi over 4. So this line becomes this line sitting here. So there would be, this is the point pi over 4 comma 0, that's this point down here. And here would be the point where we have pi over 4 comma 3. So there's the point pi over 4 comma 3. That's this point right here. And all of the other points in between get mapped along that line between them. Okay. So just putting in one more line, let's look at the line where r is equal to 1. Let's grab this line right here where r is equal to 1 just to kind of solidify this. And that's everywhere where the radius of this cone is 1, and that would be this band along here. So that's the band where r is equal to 1. That corresponds to this line here. So we've seen what happened to some points and some horizontal and vertical lines. And so the point of this example is to show you how under the transformation you could think of taking and molding this space. In fact, I'd like to do one more. Let's look at everywhere where r is equal to 0. So I'm going to need one more color here. This isn't going to be very pleasant. Let's pick maybe brown here, since we haven't used that. So here is this brown line right here, which everywhere corresponds to where r is equal to 0. And this entire brown line gets morphed to just that single point right there. So I want to return to what I originally said about thinking about a transformation as morphing space. So we're going to take this almost this rectangular sheet of green paper here, and we are going to fold it into 3 space according to these rules up here. These are like the origami rules telling us how to map this, how to mold this piece of paper. So you're going to take this point and all these points along here and collapse them down into this single point. And then you're going to take and affix this end right here over to this end over here. And that actually is how you would literally take and fold a piece of paper into a cone, with the exception of in real life, we can't actually collapse that whole side of a piece of paper down to a point, but we can mathematically, again, by this transformation.